techniques. Um, he has explained his research to technical audiences in international conferences and non-technical audiences at school events and on local radio. So here he goes.
Hi there, can you hear me? Okay, that was kind of a funny intro, because I don't know where that came from, but I did do all those things. I'm going to talk a little bit about those during this talk. As I said, I'm part of Pivotal Labs. I'm a data scientist there. Pivotal Labs has offices around the place, including San Francisco and Palo Alto. If you're interested in what Pivotal does as well, including open sourcing our Greenplum and Hawk databases, come talk to me afterwards. That's not what I'm talking about today. And I just put my slides up on Twitter if you want to have those later on. So what I'm going to talk about today is something that maybe doesn't get enough attention in sort of data science circles, but it's something that is a big problem that faces quite a lot of us. And that is how to operationalize and put into production the models we're building. And you know, at a recent Microsoft research report said that 8 of the 16 data scientists they interviewed at Microsoft are involved somehow in operationalizing models. So these aren't data engineers or dev or ops people. These are people who call themselves data scientists but are actually doing operationalization and production of machine learning and data science analytics models. So what I'm going to describe today is a few of the sort of techniques that software developers have come up with recently to sort of alleviate some of the pain they found in putting applications into production, and how I think maybe data science can use some of those techniques in the future. But first I'm going to go through the sort of history of my career and this path that I've been taking towards this idea of cloud-native data science. And it kind of all starts with my first computer, which is an Amiga 500, which I think my parents bought for me when I was about 8. And my first programming language, but I think it was this one, so it's Easy Amos, which is a variant of BASIC that used to live on the Amiga. And this is my first encounter with the problems with packaging and deploying software, because I'd written this like amazing Star Trek blaster game, and I couldn't give it to my friends because the language was interpreted and they didn't have the interpreter. So I built something brilliant, and I couldn't package and deliver it to anyone because they didn't have the right tools and we didn't have the right dependencies. If you fast forward a few years, I was in academia doing sort of research, numerical computations of the early universe, and found out, what, if any of you are in academia, you probably know, if you're not in a computer science department, a lot of people are self-taught programmers in academia. And this leads to a lot of bad code, I think it's fair to say. So the kind of code that's, write once, run once, and that people tweak in the comments to change the functionality between runs. So if you want to run, function A or function B, just comment them out and run it again and see what happens. And as a postdoc or as a researcher, this was like the scariest thing anyone could ever say to me. Ask me like, which version of your code and which version of your data, even more scarily, was used to produce this figure in your recent paper. Because none of us use version control. We had some scripts, and we had figures in our papers, but if anyone ever asked for them, we'd kind of go, well, you don't really want to see it. And this is kind of sort of completely against the goals of science in general and the kind of reproducibility you want to have there. And fortunately nowadays science and computational physics has kind of progressed a little bit further down the sort of path of reproducibility. And some of that is due to this group, Software Carpentry, which is a great resource, first like online notes, and then running workshops in universities. And so I was introduced to these guys and I learned a lot from them. And their plan is to try and bring practices from industry in software engineering into academia. So, simple things like version control, testing, how to set up packaging, that kind of stuff. So I learned a lot from these guys. I was fortunate enough to help out at one of their workshops in London, the first one. There's now a data carpentry, which is kind of doing the same thing for data analysis skills. So, if you're in the bioinformatics department in a university and you don't have much of a computing background, maybe you can pick up some skills on data analysis. So after learning a bit about that, and in the course of my research, I decided I wanted to sort of package up some of my work, release a package. This is kind of like one of the main outputs of PhD was this package of numerical basically a numerical library to run simulations of the early universe. And they started coming across all the sort of standard problems with doing that. How do you specify your dependencies? How do you package for different operating systems or different underlying compute environments? How do you deploy this, and how do you deploy it over across maybe a distributed cluster? All those kind of things. So I was kind of learning the hard way that this is a big problem in software engineering. When I left academia and became a data scientist and started working in industry, I thought, oh great, I'm working in industry. They've got all these problems solved. I'll go there and everything will be really sort of hunky-dory. Well, it didn't quite turn out that way. The first sort of stage of my career as a data scientist was working on a lot of big systems where there's a piece of hardware that has to be installed somewhere. You might sit around waiting for that to happen. You might even wait for someone to order the right cables. It's been known to happen that the wrong cables get delivered with your big piece of kit, and you wait around for another month. There was a lot of scripting and glue code put together, and people doing manual deployments, the sort of thing that you do it once, you know how to do it, and if someone asked you to do it the next day, you'd be okay. But if someone came back a month later, you'd really struggle to do it in the same way. You'd have to figure it out all again manually. And one symptom of this might be lots of cron jobs. Like I use lots of cron jobs, but if you're something that you think should be reactive to a change in scenario, but really you just set it to go every 5 minutes instead. So that kind of brings me up to where I am today as part of Pivotal Labs. Labs has been around for 25 plus years doing agile software development. So they've learned quite a lot about how to do that and what the sort of best practices are. And things like continuous improvement. How do I get fast feedback from my app and from my process so that I can continue to build and make better software and transform the way people make software. A lot of test-driven development and things like continuous integration, where everyone on the team works together to put all your code together every day, rather than wait and have branches that live for days or weeks. And continuous delivery, so that you try and deliver software, multiple times a day, maybe up to 40 times a day is what we heard Netflix doing yesterday. And one of the main sort of things that has come out of this is this idea of a cloud-native application, and that's what we're going to talk about next. And what does that mean, first of all, for software engineers, and then maybe for data scientists? So what does cloud-native really mean? Well, in a nutshell, it's kind of this philosophy that here's my source code, run it on the cloud for me, I don't really care how. I don't really care what version of Ubuntu you're running. I shouldn't be bothered by the fact that there's been this new exploit in OpenSSH. Someone should just take care of all of that for me. And to me, this sort of rings even more true for data scientists than for developers. As a data scientist, I really, really don't care how my code is run, as long as it runs properly and gets me the results I want. So that's the idea behind cloud native. But another way to think about it is in terms of how software development has changed. So in the past, you might have reliable infrastructure. That's what those big metal boxes are for. You pay a lot of money to have the very, very best kit, because any downtime is losing you money. Nowadays, though, you assume you're going to have very fragile infrastructure. So you assume things are going to break. And the example of Netflix, again, where they have the chaos monkey that goes and randomly kills processes on their system, because when a process fails for real, you'll be ready for that, because your system is completely reliable, and you understand what the failure modes are. So again, you're going from an environment where people used to release code every 3 or 6 months. Before sort of delivery over the internet, you might get a box of disks that would update your system. That's only going to happen every few months. But nowadays, you're releasing code early and often and all the time. So multiple deploys every day. This idea of disparate responsibilities, and it works in my dev environment on my laptop, but when it goes into production, it just doesn't work. Well, that's not my problem. And that kind of conversation is just sort of not something we should be having anymore. And so the idea of DevOps is really not that you have one person that is developer and operations, but you bring a team together from dev and ops that can work together and have shared responsibilities. So the team that actually writes the code, that builds the app, is the team that runs the app as well. So they're the ones on the hook if things fail. So you kind of have this shared responsibility, which means that you, as a developer and as a data scientist, are invested in the thing not breaking, so you don't get a phone call at 2 a.m. on a Saturday morning. And then the final one is the difference between tightly coupled and loosely coupled systems. So instead of building big monolithic systems, we now try and build smaller parts that each have a distinct function, and they can be independently updated and upgraded. And whereas in the past you might have had to wait for all of the sort of smaller parts in your big monolith to be updated together. So what are the implications of this kind of thinking? Well, we just said you've got to build for failure. You've got to understand things will fail, so let's build for that and understand it. Let's make our app or our model disposable and scalable. So, you know, cloud, the whole point of moving applications and computations to the cloud is that we can scale up to large volumes and large computations very quickly, but we also want to be able to scale down. So you have to make your apps disposable and accept the constraints of the platform, whatever that they are. So if the platform says you're only allowed to do this, you're only allowed to connect to this data source, and work within those means, so because that's the way the platform is going to deliver the reliability and infrastructure promises that it's made. So one way of doing this has been encapsulated by some guys from Heroku. Is this idea of a 12-factor app. And I encourage you to go to the website and read the detailed descriptions of what each of these things, each of these sort of ideas, the factors mean. I'm just going to call out a few of them here because they kind of go back to that story I was telling of what I've been doing during my career. So your code should have one code base with revision control. So definitely version your code, but don't have separate code bases for dev and test. Keep them all together and just work off one. Explicitly declare all your dependencies. So don't assume anything about the underlying platform. Don't assume that you have you know, this package installed or this version of that installed unless you've explicitly told someone you're going to do that. To enable the kind of scalability and disposability, you want to have stateless processes. That means that your app doesn't actually have any state, doesn't sort of store any data internally. Any data that it has, it gets from external data sources and puts back into external data sources. That means if it shuts down, if it fails for some reason, there's no sort of missed connection. So if I was, you know, buying something from a retail app, if that app had local state about whether my purchase had gone through or not, if the app is, you know, torn down or the VM stops for some reason, which can happen, say if you're using AWS and you're on a spot instance, your VM can just disappear without you knowing about it. If you're in the middle of that transaction, your sort of transaction will be left in kind of some zombie state. So make sure that your stateless process knows the data is either in one or more connected data sources. And then they stress very strongly this idea about parity between your development and production environments. And the point of this is that you don't get some nasty shock when you move from dev to production. So you don't have this problem of, well, it works on my laptop. You know, it works on my laptop, but doesn't work over here. So these are the ideas of, you know, 12-factor apps. Also, this whole idea is kind of called cloud-native applications. But why is that useful for data scientists? Why should we even think about it as a data scientist? Well, these are the kind of things I hear from data scientists in my day job and clients. And things like, how do I speed up the setup of my system? How do I keep all those different versions of Python and R and all the libraries and everything? How do I keep all that together? Like, how do I know which version works with what? How do I make my production and dev systems the same? And maybe more specifically for data science, how do I make my models easily available? And how do I make repeatable model and reproducible model runs? So kind of getting back to that, the idea of science as being some reproducible activity. If you want to run your simulation again, if you want to run your model again, how do you do that? So this is kind of my starting sort of idea of what cloud-native data science might look like. This is by no means sort of finalized, and it'd be interesting to have a conversation with everyone here and sort of more widely in the community about what other aspects are needed. I think we need the 12 factors from just normal software applications because that's kind of what we're building. But also this idea of reproducibility. So let's keep all the inputs for your model. Let's maybe keep the state of the random seed when you start a stochastic process so that you could rerun it again if you needed to figure out, to debug a particular result or to figure out what happened. The kind of single unit for data science and machine learning is a model that has some output. Maybe those are the things we express as services. So you can have models talking to each other and then talking to the wider community or the wider application that they live in. And as well as explicit configuration for the dependencies, I think data pipelines for us are the thing that we need to explicitly write down. So the kind of thing that some people now may set up sort of manually, this dump from this database or this, HTTP stream, and I'll do this, I'll run this cron job that runs this Python command, do that, and then dump it into HDFS. If we can have an explicit format for that, that's written down in code, then you can version that as well, and you can keep that with your model so that you know what version of the pipeline produced what version of the model. But there's lots of other things I'm sure we could add to this list. So, if you have anything that you think is part of this list, come and talk to me afterwards. So I'm going to focus on two software projects that I've used recently that kind of help with some of these things. The first one is Cloud Foundry for focusing on the provisioning of applications and deployment. Cloud Foundry is a platform where you can push your applications in a variety of different languages, and they'll get set up the way you want and basically do that, run the source code for me, I don't care how bit. This is kind of the platform that's underlying a lot of different things, including the Intel Trusted Analytics platform that we heard about yesterday, GE's Predix system, things like IBM Bluemix, they're actually all running on Cloud Foundry. But Cloud Foundry is an open source piece of software, so you can go and play around with it. There's a lot of hosted versions. What it gets you is this kind of notion of some simple way of deploying your app. So if I have a Python or Java or Ruby or a few other types of apps, I can actually just push it, and Cloud Foundry will determine that this is a Python app. It will go install whatever it needs. It'll go install a Python interpreter. You'll tell it all the dependencies, all the packages. It goes and installs all of those. It provisions any data sources, maybe like a Redis queue or something, and will bind that to your app. So that's where your stateless app can get its data. And then it handles all that kind of annoying stuff about creating subdomains, routing, load balancing, all that kind of thing, and handles all that for you and creates an application that lives on the internet or in your internal system. And kind of the clever bit here is then it continually checks the health of your application and will restart it if anything goes wrong. So you can scale up and out and whatever you want, but if one of these instances fails, it'll actually restart it for you. So you can kind of rely on it to sort of maintain that reliability in the face of failure. If you want to know more about this, there's not much online yet about using Cloud Foundry for data science. I've got a tutorial on GitHub you can go use. It uses Python to do a few things like deploying simple Flask apps, scaling up, scaling down, and connecting data sources like Redis, but also using Conda for the package management. So have a look at that if you're interested. And you're all taking pictures. I will have the link later on, and it's on my Twitter account as well. The other thing I want to focus on is the data pipelining issue I talked about. So how can we write our pipelines in some kind of configuration way? I've used Spring XD and Spring Cloud Dataflow for this recently. So these are services that you can use to write composable data pipelines. So there's a domain-specific language. It's based on Unix pipes, so you can have this kind of Unix pipe sort of structure where you specify, okay, get something from a HTTP server, filter it in some way, transform it, then dump it out into HDFS. And you can specify things like the port as command line arguments here, or you can have pre-specified them somewhere else in a configuration file and just have the pipe look as simple as this. You can have multiple paths, so you can like split off from this filter here and go down a new path that says, do this other transform and then dump that into Redis. So you can build actually quite complicated architectures, like this is sort of the start of a simple Lambda architecture, where you've got a fast path in Redis and then everything is just kept in HDFS as well. You can kind of build those up, but keeping all the configurations so that you know what that looks like and you can reproduce it very simply. There's a lot of integrations for this, for Spring XD, including lots of different sort of transport layers like Kafka and Rabbit, lots of different transformations you can use, configuration with Spark, and in fact PMML scoring, which is kind of very handy using JPMML. So if you've created a model somewhere, you can actually score it very quickly using Spring XD. You can actually use it to do your batch workflow as well. So set off a MapReduce job or a Pig job, or even set up a Spark job as well. And it connects to lots of different things as well. So it's doing all that sort of plumbing in between your processes and doing it in a way that you can configure and keep around and version as well. So that's really all I wanted to talk to you about. As I said, I'm really interested in what people think about, what ideas we need for cloud-native data science. If you want to learn more about this novel by Kim Bear and Stafford called The Phoenix Project, it's like a fictional narrative about what DevOps is, from the view of an IT manager who's trying to get something into production. It's really quite a fun book, and the interesting thing is the thing they're trying to get into production is a recommender system. So this is actually trying to do DevOps from the very beginning, trying to do something that's kind of close to our hearts and something we would like to see in production. And there's a few more links down there, but I think that's it from me, and I'd like to take any questions if we have time for a few questions. Okay, so I think it's about 5 minutes for questions, if anyone has any questions. Yes?
So, can you maybe elaborate on what you consider needs from the cloud for data scientists that perhaps traditional software engineers and DevOps engineers necessarily need?
So I think, if you think about it, data science and like building predictive models is a form of software engineering. So, we're actually writing code. But some of those things that we want on top are not things that are interest to software engineering. So the reproducibility one is a big one for me, I think. Normally software engineers don't particularly care about keeping around all the input data that they had and the version of that, so they'd be able to reproduce something beyond simple debugging. Whereas, if someone comes to you, you've written a fraud protection model, and someone comes to you in a few months' time and says, okay, we had, you said this transaction was not fraudulent. Can you work me through your reasoning for that? If you haven't kept, the random seed for that, you don't really know why your model, came to the decision it did. You won't be able to actually dig down any further. So there's that kind of thing. There's the pipelining stuff, which I think is, a bit more elaborate than what you normally get in an application. A simple sort of CRUD app, just connects to one data source and does a few operations, might use an ORM. We're kind of normally hooked in a bit more straight into the data sources at a lower level. So, so we're worrying about things like, is it a columnar or row-based storage, or am I using the fastest version of this database, or whatever it is, have I indexed properly? And we're kind of normally worried a little bit more at low level, so kind of keeping that pipeline as configurable, sort of written out, is kind of useful, I think. Any other questions?
How limited are you by the fact that some libraries that do machine learning are not very amenable to parallelization, or the design of the underlying libraries? To me, seems like it needs maybe a bigger problem than putting everything on the cloud per se. In other words, you're limited by what the person did. Like for instance, scikit-learn is a very powerful thing, but I'm not sure. I'm not sure how easy it is to parallelize scikit-learn on a large customer. So could you comment about that interaction between things?
Yeah, I think there's definitely some problems where you can just naively parallelize things, and you can just build a model per category or a model per model per customer maybe, and then you're actually just doing small models, just lots of them at the same time. So that's kind of fairly straightforward. If you're trying to parallelize something that's a very big model across all your data at once, and yeah, the traditional small and medium data size tools like scikit-learn probably aren't as easy to use in a distributed environment. But there's a lot of new tools that do work in a more distributed way, and I think people are going to slowly start moving to those. We heard Wes McKinney this morning talk about IBIS being something that kind of reaches over that and tries to make Python usable in a big data sense. But you've got, MLlib and those kind of things, which, MLlib now uses the sort of API that looks very similar to scikit-learn. And so the kind of learning curve isn't as bad. But yeah, there's a lot of, you do have to change things in order to be able to run a highly scaled, parallelized model on, across lots of distributed infrastructure. Things do have to change. It doesn't look as simple as running something on your laptop.
Can you recommend any knowledge base that really talks about data science in the context of like an architectural framework where it's like a reference architecture.
Yeah.
You go in there and you know that if you're talking about classifications, here's a pathway of technology method. You're talking about different.
Yeah, so somewhere you could go to that says, if you have this problem, do this with this architecture. Yeah, so I don't know off the top of my head of anything that kind of encapsulates all of those things. We talked about scikit-learn there. There's a diagram that someone made for scikit-learn for if you have this much data, basically a flow chart. If you have this much data in this problem, go down to this, use this classifier, use this technique. And that's been, circulated so much because I think there was this vacuum of people didn't know what to do in each of those scenarios. Unfortunately, I don't know off the top of my head anything like that. Okay, I think I have to leave it there. Thank you very much, and come talk to me afterwards if you want to talk further.